Yeah.
She is sick.
She's so sick. So excuse.
Okay, let's get started, you guys. Happy Wednesday. Okay, so two things before we get started. First of all, I know you guys are very busy seniors and you have a lot going on, but when you are working on your pre-lab quiz for Monday, June Monday, try to look at that a little bit before Sunday. I do see emails from you guys coming to me on Sunday or probably other TA. I do check my email. It's on my phone. It's kind of like a curse and a blessing. But it would be much better if you have questions like coming in on Friday, even Saturday for me is fine. Just try to look at it. Don't leave yourself to the last minute. Oh, it's due tomorrow at 9 a.m. and I have this question. So yeah, try to do that a little ahead of time. That's one thing. The other that Laura wanted me to reiterate is that significant figures for the lab that we just had this week. When we're doing addition to determine the mean, okay, so you add all of your different reps, you add them and then you divide by the number of applications, 3 or 6. So what you need to take into account is the addition rule in this case. You don't want to take account the figures of you're dividing by 3 or 6, that it does not include your estimation of significant figures. So the addition rule goes by how many decimal points you have, and you go with the number that has the lowest decimal point. So your average will be the one with the lowest decimal point if you're following addition rule. Is that it, Laura? Is there anything else I need to? Yeah, okay, good. And if you have any questions, I know it is not intuitive. Sometimes these significant figures will walk you through it. Sometimes we just say, you know what, just report 3 significant figures are possible when it's too complicated. But yeah, try to follow rules as much as you can for this lab and ask if you have more questions. Okay, so today we're going to do a lot of calculations. I don't know about you, but I love calculations. But maybe not all of you do. So we'll walk through this very slowly, and a lot of it is general kind of information. A lot of it is revision. As food scientists, whether you are going to be a researcher in a lab or you're going to work at a company where you have to do some lab work, you would need to prepare reagents. So it's kind of like first thing you do in any experiment. And to prepare reagents, you really need to know how to do that. Like what is the molarity and how we get that? How do we convert percentage to molarity? How do we convert molarity to normality? This is all important. How do we dilute? How do we prepare a buffer? So this is gonna, be in your career somewhere along the line, unless you do something completely different. But it's good to know. It's good to know how to prepare reagents and buffers and dilutions and all of that. So a lot of calculations go into that, and we'll have a lot of practice. So I would like you to take a piece of paper out, and you will get a +2, I believe, for what you work on today. And although you're going to turn it in, take a picture of it before you give it to me so that you have the calculation when you want to study. You will have the calculation. Be as detailed. Don't wait for the answer and write the answer down. You don't get the credit for doing that. You want to show the equations and calculations, and then take a picture at the end. Okay, I'll give you all the time you need to think about them and work through them together. Okay, you do need a calculator, or you can use your phone. All right. Buffer. Buffers are used for so many different purposes, but the most important question. Are you gonna answer? You ready to answer? I'll call you in a second. So buffers are used for mostly to stabilize a pH. So sometimes you need to stabilize your pH for an enzymatic reaction, for a chemical reaction, for running samples on chromatography. So where you really want to make sure your pH doesn't change during the reaction. So that's where buffers are used. Okay, so what is a buffer? It consists of a mixture of weak acid and their conjugate base. Sometimes we call it salt, it's salt, or conjugate base. It means the same thing. Has a neutral pH, stabilizes a certain pH. I already gave you one of those. So Tyler, what were you doing?
I'm going to say A and C.
Tyler's going to say A and C, and this is correct. So you can have any pH. It can be acidic pH, can be neutral pH, can be low basic pH, it doesn't matter. It can be any pH based on the needs of the reaction. So that is not correct. It does stabilize the pH, and it's a mixture of weak acids and conjugate base, because when you have a weak acid, it's going to give you your proton. If there is anything basic in the reaction that might want to raise your pH, then the weak acid is going to give it a proton to stabilize that. If your reaction is causing the formation of components that are acidic and will reduce your pH, then your conjugate base is going to capture the protons from your reaction and stabilizes the reaction, the pH of the reaction. Okay, so this is a working slide. This is reminding you here of the molarity. So you want to remember molarity equal number of moles over a liter or per liter of solution. So this is something you have to remember. We're going to use it a lot. Molarity equals number of moles per liter of solution. And number of moles equals the mass by the molecular weight. And the molecular weight is grams per mole. Okay, so these equations you will be using a lot. Normality is another form of concentration, which is basically equals the number of moles equivalent of a solid. What does the number of moles equivalent mean? So the moles that are being transferred within a reaction. So for example, in an acid-base reaction, there is H plus and OH minus that are participating in acid-base reaction. So these would be the equivalent moles of solute. So if I look at H2SO4, it has 1 mole of this has 2 molar of hydrogen or H plus. So 1 molar has 2 normals. Why? Because it has 2 hydrogens. So therefore, 1 molar of H2SO4 equals 2 normal of H2SO4. HCl, for example, has 1 proton, 1 H plus. So normality equals molarity. Anyway, H, normality equals molarity. You have 1 OH. Calcium hydroxide. Normality equals twice molarity because you have 2 hydroxyl. These are just examples. Equivalent weight is important and will come back to us when we cover titratable acidity chapter later on. Every acid, organic acid, has different groups of carboxyl groups. So acetic acid has 1 carboxyl group, citric acid has 3 carboxyl groups. So equivalent weight would be divided by the mole equivalent of the solute. So if I look at H2SO4, the molecular weight of H2SO4 is 98. Then you have 2 H's. So the equivalent molecular weight is divided by 2 is 49. This will be relevant later when we talk about pH and titratable acid. Percent concentration. So it can be weight by volume, which means, for example, grams in 100 milliliter, that's a percentage. weight by volume, or it can be volume by volume or weight by weight. So it could be volume by volume, meaning milliliters per 100 milliliters, or weight by weight, grams per 100 grams. Concentrations sometimes are much less than 1%. When they're much less than 1%, we don't refer to them, we don't use the term percentage, we start saying parts per million. So parts per million means milligram per kilogram, or micrograms per gram, or if it is weight by volume, would be milligrams per liter or micrograms per milliliter. That's a part per million. Or you have a part per billion. Why is this important and relevant to us? Because, for example, in HPLC, we can calculate concentrations as low as parts per million. In GC, we can go as low as parts per billion. And with more sophisticated instrumentation, we can get concentrations as parts per trillion. This is an important equation that you will be using a lot for determining dilutions protocols, or you will be using it later for neutralization equation. We're going to be doing a lot of neutralization equations when we cover different acids, free fatty acids, for example, peroxide value, percent acidity. We're going to be using this equation to calculate concentrations based on titration. So milliequivalent is defined as milliliter of your solution times its normality, because it's milliequivalent, so it will be in milliliters, equal milliequivalence of your other reactant times the normality of that reactant. If you have acid-base reaction, so that would be milliliter of the acid multiplied by the normality of the acid, and milliliter of the base multiplied by the milliliter of the base. We're going to use that quite a bit when we are doing titration type of reaction. But for preparing of reagents, this is going to be our key equation to determine dilution protocols. Oftentimes, you're going to get solutions or reagents that you buy that are very, very concentrated. So we buy a bottle of hydrochloric acid. The normality of that hydrochloric acid is 12 normal. It's very concentrated acid. But oftentimes, we want to prepare only 0.1 normal HCl, which we use for titration in Kaldal assay for protein determination. So we need to prepare only 0.1 normal from 12 normal. How can I use this equation to prepare a liter of 0.1 normal HCl from a bottle of HCl stock solution of 12 normal? So do the math and tell me how many milliliters I would need from the stock solution. Here we go, you're applying the equation. And when you have an answer, you can tell me. Just a second. Drew, you have an answer already?
Yeah.
Just a sec. Let's see. Let's give a chance a little bit longer time for others. Do you have an answer, Grace? Almost? Okay. So we're applying this equation. So we already know that I want 1 liter, so that would be 1,000 here, milliliters. And I already know what concentration I want. What I'm trying to find is how much of my concentrated solution of 12 normal I would need. Yes, Grace.
8.3 milliliters.
Yes, 8.33 milliliters. So you apply the equation, make sure you put in your units. So you have 1,000 ml by 0.1 normal, and then you divide by 12 normal, you get 8.33 milliliters. So that's what you need. Okay, now, if I ask you this question in a quiz, I want you to tell me, not just show me 8.33 milliliter, to tell me how do you go about it? You get a volumetric flask that is 1,000 liter volumetric flask. You put a little bit of water in there, distilled water, because you want to put a little bit so that you can pour the concentrated acid on it. Instead of putting the acid, you don't want to pour water on top of a very concentrated acid. It splashes. It's not safe for you. So you always put a little bit of water. You put in your 8.33 milliliters. The way you do it usually is you pipette. You can use mechanical pipette. We do 1 milliliters, or we have a 5 milliliter pipette. You do 5 and then 3 ones, and then you dial down to 33 milliliters or 330 microliters, and you add that, and then you mix a little bit, and then you make up to the volume on your volumetric flask, the mark. So there, then you have your 0.1 normal HCl. Great. So this is practice of calculations again. Calculate the number of moles you have of calcium in 25 grams of calcium chloride to hydrate, or 2 moles of water. So I'm going to give you some givens. So you remember the molecular weight of calcium? 40. Okay, molecular weight of chloride? Close, 35.5. Water, well, H2O is 18, but anyway, hydrogen is 1, oxygen is 6. Don't worry, in a quiz, I will give you those. You don't have to remember them. What's that? I would, like, if I have a question, I'll give you the molecular weight of the entire month. Here, I'm giving you the individual that you can calculate for the entire month. Give it a go. You are after determining number of moles of calcium in 25 grams of calcium chloride hydrate.
And then Avogadro's number.
Say that again?
Avogadro's number.
You don't need the Avogadro's number. Yes, Michael?
Purine is supposed to be like multiplication. I don't know. Calcium chloride dot 2 waters.
Oh, that is not a multiplication. You add all the different molecular weights to get the molecular weight of the whole molecule. It's a molecule. That's telling you that the calcium chloride is attached to 2 moles of water.
Normally how they do it is it's like when you do like a hydrated compound, you put it in parentheses.
Yeah.
And
Yeah.
so
I mean, yeah, I'm old school. This is what we used
yeah,
to do.
I don't know, that's what we learned in Since I learned it.
Yeah,
Okay,
I
so it's
learned-
like you put it in parentheses, so that way like it's specific for water, because water likes to hydrate.
I
And it's just
understand.
like having 16 water, you're writing out like age 20 or age 32 or whatever.
Yeah, here I didn't put it, but usually 2 means 2 moles of water.
Yeah. Like,
Yeah,
it's just a different-
imagine you have friends.
It's just a different.
Okay, are we discussing points or do we have an answer? Shri,
I got 0.17.
what's that?
0.17.
0.17, correct. So the molecular weight of calcium chloride with 2 moles of water is 147 grams per mole. You just add them up. And the number of moles, you have 25 grams of this molecule. So that's the mass, that's the molecular weight. So you have your units, grams, and here grams per mole. So grams will cancel and moles will come up. And then that would be 0.17 moles. So you have 0.17 moles, given that it is 1 calcium. So it is 1 equivalent to the moles of the entire molecule. So it would be 0.17 moles. Any questions? Okay. How would you prepare 1 liter of 0.2 molar? Okay. If you have questions, don't be shy, just ask me. We can go over it together. I'm sure if you have a question, some other student might have the same question, so it will benefit everybody. How would you prepare 1 liter of 0.2 molar NaOH if you have 2 different stock solutions? So you have 2 cases here. Each one is separate. So let's start with a case where you have 3 molar NaOH. You have a stock solution of 3 molar NaOH. And in another case, you don't have a stock solution. You actually have the pellets. NaOH come in pellets. So you have, well, actually in this case, not pellets. It's a solution prepared as 45% weight by volume NaOH. Sorry, excuse me, not pellet. It's another stock solution, 45% weight by volume. Forget what I said about the pellet, so you don't get confused. All right, so solve the first one and then attempt the second. Any answers you have so far? Do you have an answer for the first one? Lenny? Say that again, 66 point milliliters. Yes, so from the first one, it is 66.7, we rounded, to of 3 molar NaOH. So again, you apply the equation of N by V equal N by V. We want to prepare 1 liter of 0.2 molar. Molar or normal, in this case, it's the same because you have 1 OH. And you have your 3 molar stock solution, and then you will not want to know how many mils of that you want. So when you solve for X, it will be 66.7 milliliters. Again, you complete your answer by saying I would get a volumetric flask, 1 liter, put some water in it, add the 66.7 milliliter, and then mix and make up to a volume. All right, let's do the next one. Anybody got that far? Not yet? Think about it. So first thing you'll see is a different unit. So you have a percentage here, and you have a molarity here. So you want to convert this percentage to molarity. That's the first thing you want to do. You want to make sure your units are the same. So this is 45 grams per 100 ml, weight by volume. So this is what you want to put. The given is 45 grams in 100 ml. That's your stock solution. You want to get the molarity of the stock solution. So what you need the molecular weight of NaOH. So sodium is 23, oxygen is 16, hydrogen is 1. This is 40 grams per mole is the molecular weight. Okay, so you have the molecular weight of NaOH, you have the percentage grams per 100 ml. Using this data, how can you convert that to molarity? What would you do? You have an approach you would like to share? Michael?
We're gonna cancel out the grams, it looks like.
What's that?
Cancel out the grams first, the weight. Because wait, do we want grams for?
So I want to convert this unit to molarity. Okay, so how do I convert this to molarity? Anybody that, okay, Drew.
You wanna, I guess you could do, I can't remember what it's called, you do like the scientific way, like if you do like 45 divided by 100, right, if you multiply or divide it by 40 over 1 mole. 1 mole divided by 40 grams. That way, then you should end up with 1.125 moles divided by 100 milliliters.
I think you're on the right track, but there's some unit confusion a little bit. Ellie, what were you going to say?
Well, something similar, but the way that I wanted it is, you have 45 grams in that liter. So if you
In a
do-
liter?
Yeah,
You have 45 grams at 100 ml.
yeah. So,
But so what would you have in a liter?
well, I was just gonna say that you can divide it, this 45 grams, you can divide that by the molar weight, which is 40. And you can get however many moles, which is 1.5.
Okay, but we want to remember something. Molarity is per liter. Right? So you might be doing the math differently.
So you just need to like, I know this is like the quicker way to do it, you just put the decimal over 1 more.
Yes.
Or multiple.
0.112.
The other way, it would be 11.25.
You'd want to multiply by 10.
You want to multiply it by 10.
Or you, yeah.
Okay, because this is 445 grams in 100 ml. If I have 1,000 ml, this is going to be 450 grams. Right? So 45 grams in 100. This is going to be 450 grams in a liter. And molarity is per liter. So I need to know how many grams I have in a liter. I know you guys do the math differently. I'm old school. This is how I think about it. So I just multiplied by 10 here and here so that I get 450 grams per liter. Okay, so now I have the mass in a liter and have the molecular weight, then I can get number of moles, which would be 450 grams over 40 grams per mole. Then I get the 11.25 moles. Then that means I have 11.25 moles per liter, which means 11.25 molar. So the trick here for you is to convert the units. And always remember, molarity is in a liter. So if this is a percent, that means it's in 100 milliliter. So I need to multiply by 10, so I get it in a liter instead of 100. I want it in 1,000. So I convert that to grams per liter. Then with the molecular weight, I can get the number of moles, and the molarity will be number of moles per liter, because I already converted it to a liter. Then that's 11.25 molar. Now my stock solution is 11.25 molar. Then I apply the same equation I applied earlier here, which is N by V equal N by V. What do I get in terms of molarity? And Drew, go ahead.
It would be like 17.8.
Absolutely correct.
What about the sig bit? It's like,
Ah,
because would you have?
yeah. You know, don't go there.
What if you give 20 then? Because you're asking for 0.2 molar.
20.
But like if you look up top, it's.
Yeah, I mean, it's 20.20.
Oh, okay, you just didn't type the X.
You don't go there. It's not a significant figure lesson. So we're not taking into account any accuracy of a balance here. So when we're doing this in the lab, then we can think of, okay, what is the accuracy of my balance? What's the accuracy of my volumetric flask? Then I can determine significant figures. So for now, just take these numbers as okay. So like I said, we convert to per liter, and then we convert the mass to moles, and we get 11.25 moles, which is molarity per 1 liter, which we already converted to 1 liter. And once we have that, then we apply the equation, and then it would be 17.8 milliliter, and make up to volume.
So if the reagent has two moles, you read by class 2.
If the reagents have what?
2 normal.
OH. If the reagent has 2 OH, then you have to convert molarity to normality if you're given normality. If you're given molarity, you divide by 2 to get molarity. Yes. And then that would be the case in calcium hydroxide, for example, which has 2 hydroxyls.
We were like for B, I'll say instead of we're solving for 1 liter, let's say we were solving for 100 milliliters.
Instead of putting 1,000 here, you put 100.
Yeah.
Or
so
sometimes you're preparing 250. you, so I'm gonna be paying 500.
So like you gave us, it was 45 grams per 100 milliliters. So instead of, because you're converting it to 1,000, because we need to have to prepare 1,000, right?
No, the converting to 1,000 is to convert the units to molar.
Oh, because is it like,
It's the molarity is moles per liter, so I'm converting to 1,000 so I can get the molarity. But if I want to prepare 500, the molarity stays the same. Okay, you change this value.
so like when you actually like the unit of molarity is moles divided by liters?
Yeah, the unit of molarity is moles per liter. Absolutely. Yes, Tyler?
Is weight over volume always grams over?
Yes, the weight by volume percent is grams per 100 milliliters. All right, this is a little bit more complicated. Here you are given a reagent that comes to you as a percent volume by volume. And this is common for H2SO4, which is sulfuric acid. And in this case, the bottle tells you when you order it from the store, it came and says it's 98% volume by volume, which means 98 milliliters per 100 milliliters. So you have the volume here. You don't have the mass, but I'm giving you the density. The density, which not I'm giving you, you'll find it on the bottle. You'll find the density of H2SO4 as 1.84 grams per milliliter. And now you want to prepare 0.1 molar, and this is the given that you have. You have the percentage weight of volume by volume. You have the density. And in this case, Drew, you're preparing 500 milliliters of 0.1 molar H2SO4. So I have this information, this and that. I want to determine the molarity of the reagent I have. All I know, it is 98% volume by volume, and it has this density. How can I use these numbers to get the molarity of that reagent? And I'm giving you, to help you, that the molecular weight is 98 grams per mole. The molecular weight is H2SO4. So give it a go for the remainder of this time. Hopefully we can answer it, and that will be the last thing for today.
You said like volume per volume, you said it was like 98 milliliters.
Yes, the percentage is percent, that per 100. It's always like per 100. You're done? Oh, you did it, Tyler. Okay, good. What did you do? Tell us your approach.
So I went from 98 milliliters over 100 milliliters to milliliters over liter.
Okay.
Then on the top side, I went from milliliters to grams, grams to moles, that's molarity.
So how did you convert your milliliters to grams?
You get that.
You get that. So density is mass by volume. And if I have the density and I have the volume times the mass, volume times the density, sorry, gives me the mass. Okay, is that what you did?
and then grams per moles, and then use that.
Okay, very good. What is the final number you got?
I got 2.7
2.72.
milliliters.
Yes, but what was the molarity of your starting reagent?
Oh,
Absolutely. Very good. How many of you got into 18.4? Very good. And Laura, you had a question?
You're gonna get still the weight for 100 ml, so you don't have to put that 1,000 ml.
So either you can do both ways. Either you convert to liter or you convert to mass and then convert to per liter. You can do it either way, you'll get the same answer. Yeah, so really it's up to you. Either you go from 98 milliliter per 100 and then say 980 milliliter per 1,000 milliliter, and then you convert to grams, or you can convert to grams and then calculate per 100 milliliter. Either way, you get the same answer. Okay, all right, so I'll show you the calculations then. So the way I did it here is I converted to grams from the beginning. Okay, so I said, okay, how many grams I have in 100 ml if I have 98 mils in 100 ml? So 98 milliliter in 100 ml, the density is mass over volume. Then this means if I multiply volume by density, I will get multiplying volume by density, I will get the 180 grams. So there's 180 grams in 100 ml. So this means in 1,000 ml multiplied by 10, I get 1,800 grams. So now I have 1,800 grams in my liter. If I want to get the molarity, so molarity equal number of moles over volume. Volume is my liter, so number of moles is mass over molecular weight. I have the mass now, and the molecular weight is 98. Then I get the 18.4 moles, and molarity is per liter. So I did all that calculation per liter. Now I have the molarity, now I have equiunits. I want 1 molar from 18.4 molar. Then I use the M by V equal M by V. And then I get the 2.72 milliliter. Because in this case, you put 500 ml. The question is asking 500 ml. So you want to prepare 500 ml of 0.1 mole. So it's not a liter. So look at what the question is asking. Okay, so then you get that. Solve for X, 2.72. In this case, you want the 500 milliliter volumetric flask. You would put a little bit of water. You add this 2.72 and make up the volume that way. Okay, so you hold on to your paper for next time, and I would like you to think about this one. This is a dilution problem. I would like you to kind of solve it, and next time we come in, that would be the first thing we talk about. But give it a go on your own, okay? Good. 3 minutes early. Can go.
So that's the last slide. Okay, thank you. Yeah. Yeah, that's just
Where is it?
I'm gonna stop during the lab.
Yeah, I can answer just, I want to stop the record.